Hey, hi there. In today's video, we'll be discussing about probability and the various concepts which are associated with this particular parameter. Okay. So the previous video, we talked about descriptive statistics, and today we'll start off with probability and their concepts. So if you look at the session agenda today, we'll start off with probability, its meaning and other concepts associated with it. The rules for computing probability, like multiplicative and addition rule, I'll explain to you properly. We'll also discuss about some other different kinds of probability which we calculate in more complex data like marginal probability, conditional, and joint probability as well. So let's start. So we talk about probability. What does probability mean? Probability refers to a chance or likelihood of a particular event taking place. Now let's go through some of the nomenclature which we typically use when it comes to probability. What is an event? Event taking place, right? Suppose when I toss a coin. So tossing a coin is an experiment. And what does a coin toss give you? It may either give me a head or a tail. So head and tail are outcomes, are events of an experiment, but either one of them can happen in one experiment. So if I toss a coin, the outcome is either one of them, and both have a 50% chance of occurrence. So an experiment is a process that is performed to understand and observe possible outcomes. So it's a process that is performed to get certain results or possible outcomes. So when you talk about head and tail, these are possible outcomes. Okay, head and tail are both possible outcomes. We do not know which one will happen exactly. So that is why we're talking about a chance or likelihood. When we talk about probability, we typically refer it to as a chance or a likelihood rather than taking it as a result. Right. So we talk about chances. So set of all outcomes of an experiment is called the sample space. So your head and tail, when you toss a coin, your head and tail is the sample space, because this space consists of all the possible outcomes of the experiment, which is tossing a coin. So if we talk about probability, what does probability mean? Numerically, it means the ratio of the number of favorable occurrences divided by the total number of outcomes, right? So if we talk about head and tail, this is my sample space, right? And the number of such possible outcomes is 2. So when you toss a coin, in one single coin toss, either a head may come or a tail may come. So both of their probability will be 0.5 and 0.5. So what's the probability of a head when we toss a coin? The answer should be 0.5, because the number of heads which we can possibly get when tossing a coin is 1. Or the number of tails which can possibly get when tossing a coin is 1. We cannot get 2 heads or 2 tails when you toss one single coin. Okay, and probability will always lie between 0 and 1. 0 probability means there is no chance of that event occurring, and 1 probability means every time you do the experiment, the probability will always be the outcome of that experiment. That's why its probability is 100%. What's the probability of me getting a head or a tail when I toss a coin? The total probability is 100%, because either a head or tail will definitely come. Apart from head and tail, there are no other possible outcomes. But if I ask one of them, probability of one head occurring, then that will be 50%. Clear? So I'm giving basic examples here just to introduce you to the concept of probability, and slowly and steadily I'll give you much more complex examples and scenarios, more interesting scenarios rather, so that we can extend our knowledge on this particular topic. Whenever we talk about probability, there are 2 kinds of axioms, or what you call as theorems, which come to my mind. Whenever we have complex scenarios where we have to calculate multiple probabilities of multiple events, how do we analyze those probabilities, right? So the first theorem which typically we come across in the chapter of probability is mutually exclusive events. What are mutually exclusive events? 2 events are mutually exclusive or disjoint if they cannot occur at the same time. A clear example is the set of outcomes of a single coin toss, which can result in either heads or tails, but not both. It can either result on a head or a tail, but both of them simultaneously cannot happen. That is why we asked the question, what's the probability of a head or a tail coming up? That will be 100%. What's the probability of a head and a tail coming tail result simultaneously? The probability will be 0. Right. So if we think about mutually exclusive events, right? So suppose I have two set of events, say A and B. This can be easily explained with the help of a Venn diagram. Venn diagrams are something which we had covered in probably class 9 and 10. Right. Suppose this represents A event, and this sample space represents B event. Right. If I'm trying to ask for mutually exclusive events, if I want to find the probability of both these events, happening simultaneously, then the probability will be 0, because you can see here there is no common point here. However, if I want to find the probability of either one of them happening, then we can definitely add. What's the probability of a head or a tail occurring? Of course, that we can add the probabilities and get the result, which is 1. Right? Okay. Whereas for non-mutually exclusive events, which means that they do share some common ground, that is where my equation, my formula changes. That is where the concept of intersection comes in, because both of them share some common ground. And if we want to find out the total probability, we cannot just simply do PA plus PB, because we have some common ground and we have added this region, this intersection region 2 times when we added PA plus PB till here. So I have to subtract the intersection point 1 time once. That's what we are doing here. So for mutually exclusive events, my P of A intersection B is 0, because there is no common ground here, right? Then total probability will be the summation of the individual probabilities. Simple as that. Okay. For non-mutually exclusive events, however, when you try to find out total probability, we have to subtract the intersection part from total summation of these two probabilities, because they share some common ground. That is what is mutually exclusive events. We'll try to explore all these concepts with more examples. Don't worry about it. Next, we have independent events. Now, here we saw that is A and B, right? So next concept comes in what is called as independent events. So two events, A and B, are said to be independent if the occurrence of A is in no way influenced by the occurrence of B. Likewise, occurrence of B is not influenced by the occurrence of A. So we have two events, A and B, and both of them are said to be independent when A and B do not have any dependence on one another, right? And if we look at it, it's this. So for independent events, the outcome of one event does not influence the outcome of the other, right? Both of them are independent events, and that is why we can multiply the probabilities. We can multiply the probabilities together, okay, directly. I'll give you an example. Let's say I have 2 coin tosses. Okay, I'm tossing 2 coins, and both these experiments are not dependent on each other, right? So coin 1 and coin 2. So what's the probability of 2 heads occurring when we toss 2 coins, right? So this is event A and this is event B. So probability of event A, which is head, right? Head experiment is 1, but the event A, which I'm talking about, is for heads. Event B, what I'm talking about, is for heads from experiment 2. So probability of head in experiment 1 is 1/2, and probability of head in experiment 2 is again 1/2. And the question was, what's the probability of both heads coming up? And that probability will be half into half, which is 1/4. Right? So that is what independent events is all about. Okay. So if you go back to the previous question, in the previous theorem, rather, I would say, if you go back previous, so this value which you see here will be equal to probability of A into probability of B if they are independent events. If A and B are independent events, right? Whereas if they are not independent events, their formula will be something else. So for mutually exclusive events, the probability of dependency or non-dependency does not occur at all, because here there is no common ground at all. So the question of dependency does not arise. Many people, they generally have this doubt and have this, they're confused that they ask if it is mutually exclusive and independent, what will happen? No, when it's mutually exclusive, there's no question of dependency, there's no question of independence. There are two disjoint events. When it is non-mutually exclusive, where they share some common ground, that is where you will talk about independent independency. So now let's move to dependent events. So what is dependent events? The outcome of one event is affected by the outcome of the other event. Okay. To help you understand this question, I'll take an example. Okay. So the probability of AB is equal to, instead of equating it to probability of A into probability of B, we equate it to probability of A and multiply with something which is called as probability of B such that A has happened. So this is called as conditional probability. Probability of B such that A has happened, right? This left-hand side can also be equated to probability of B into probability of A such that B has happened. I can write the vice versa of the events. So basically this entire expression can be equated with this expression, and this guy, it gives rise to a theorem which is called as Bayes theorem. Based on this, we have a machine learning algorithm by itself, which is called as naive Bayes algorithm. But we'll go through that later on. We'll talk about Bayes theorem later on, not now. Okay. So let's focus on this first. So now, if you want to compare mutually exclusive and independent events, let's just do a quick recap of the same. Definition: mutually exclusive, they cannot happen simultaneously, right? They cannot happen simultaneously. So the intersection point is 0. Independent events, the occurrence and outcome does not control the outcome and occurrence of other events, right? So here, if it is independent, your intersection, if you have intersection point, then it will be directly the product multiplication of the product. Here, P of A intersection B will give you 0, right? Whereas either of the total probability of both the events happening will be here PA plus PB, whereas here it will be PA plus PB minus P of A intersection. And if this is independent, then this. There is no overlap, there is very simple. And if it is dependent, that is where it becomes a little bit more difficult. That is where conditional probability will set in. Independent event example. A die is cast twice and a coin is tossed twice. What is the probability that the die will turn a 6 each time and the coin will turn a tail every time? Okay. So in this question, what they're saying, they are tossing a coin and also they are tossing a die, right? A coin and a die. Die is nothing but that cubeword which you use for playing Ludo or other indoor games, right? So it has got 6 faces with numbers 1 to 6 on each of the face. Whereas coin, you can on either faces we have head or a tail. So the probability the die will turn a 6 each time. So each time means how many times you are tossing it? Twice, right? So both of the time it should toss the 6, and the probability of getting a 6 each time is 1 by 6. Just like probability of getting a tail in one coin toss is 1 by 2. And tossing it 2 times, so there'll be 2 halves and 2 1 by 6s. But they're saying both time it should give the same result. And tossing 2 times or casting the die 2 times, both of these experiments and the outcome, which is the event here we are talking about, they are not related to one another. They are not dependent on one another. The me getting the tail for the second time, the second toss, is not dependent on the first tossing of the coin. Similarly, me tossing the die for the second time is not dependent on the first, and vice versa. So we'll directly multiply these probabilities. We were asking for tail, in both the coin tosses, they're asking for the number 6 in both the dice. Number of favorable events divided by total number of possible outcomes. Possible outcomes is how much? 1, 2, 3, 4, 5, 6, 6 possible outcomes. Here we have head and tail, 2 possible outcomes. So my answer will be 1/4 for coin and 1/36 for die. So see, each time die is cast, it is an independent event. The probability of getting a 6 is 1/6. So the probability of getting a 6 when the die is cast 2 times is 1/6 into 1. Similarly for coins as well. Okay, so you're using the formula for independent events of getting simultaneous probability. Okay, now let us look at this example. So that example was an independent event example, right? Now let's take a dependent event example. From a pack of cards, 2 cards are drawn in succession. Pack of cards, 2 cards are drawn in succession, one after the other. After every draw, the selected card is not replaced. What is the probability that in both draws you will get spades? Okay. So you have a deck of cards and you pull out one card. How many cards does a deck of cards have? 52 total, right? Excluding the joker, which we did not consider in our game. So 52 cards, right? And once I draw one card out in the first experiment, I'll be left with 51 cards. Okay. So even experiment A, experiment B. The event which I'm looking for is spades. So in the first draw, when you have all 52 cards, the probability of me getting a spade will be how much? How many spades, total spades are there? So total number of favorable outcomes. There'll be 13 spades, I believe, right? 13 spades, 13 of each of these types, right? And then we have 50 total cards, total number of options which we have. Possible outcomes divided by total number of outcomes. So 13/52. Now what they are saying in the next, what will happen? You have already removed this card out. You have already removed this card out. So whether it's a spade or not, I don't care. Because again, please understand, we're talking about probabilities here, guys. We're talking about a chance or a likelihood. We're not talking about results, what actually happened. So when you draw one card out, immediately you'll be left with 51 cards. That is for sure. But what about the spades? Right? So my chances, after you pulled one card out, my chances of me getting a spade also reduced. So they also have to subtract 1 from the numerator. So my sample space or my favorable number of outcomes will reduce to 12. That too, they want spades in both the draws. In both the draws. So you have to multiply them. So this, what we had calculated, is a conditional probability. So this will be probability of A into probability of B such that A has happened. Probability of B, why? Because it's a probability of B, but such that A has happened because you've subtracted the 1 from the numerator and the denominator. Now, if we would have replaced the card back there, if we would have replaced the card back in the deck, what would my probability be? 13/52 into 13/50. Now, if you really think about it, which value will be greater? This value or this value? That is what you have to think about. If you think about this value, the outcome will be slightly greater than this outcome. Why? Because when you talk about more restrictions, when events become dependent, immediately you are imposing more restrictions. We're restricting it. We could have 13 here because now we only have 12, right? So more restrictions, lesser the probability. Okay, so 13/52 for event A, 12/51 for event B, because one card has been reduced. And I'm writing it as P of B such that A has happened because there's a condition attached to it. And that's why we'll get 1/17, right? And if I wouldn't have replaced it, if it would have been an independent event, it would have been 13/52 into 13/52, which would have been 1/16 by 4. So 1 by 17 is less than 1 by 60. So the next section which we have is on marginal probability. Okay, the term marginal probability used to indicate the probabilities that are calculated using a contingency table, also called as a joint probability table. Okay, joint probability table or contingency table. We'll talk about that. We'll discuss what is a contingency. So contingency table is what? It is consists of rows and columns of two different attributes at different levels with frequencies or numbers in each of the cells. It's a matrix of frequencies assigned to rows and columns. Again, I've given the definition what is mathematically correct. Let's take an example to understand this. And guys, we have already done this. Okay, in Python advanced module, we have already done this in pandas. When you see the table, you get to realize. So let's take a question to understand the concept. A survey involving 200 families was conducted, and the contingency table is as follows. Now, if you look at now, what is it? Now, what did my contingency table say? It consists of rows and columns. So these are my rows, and these are my columns. And what did it say again? At different levels with frequencies or numbers in each of the cells. Different levels. Levels means this is one level and this is one level. Right? So both these parameters have come from a column which says salary. Both this probably have come from a column which say, buyer or non-buyer of a car. Right? So these are nothing but categories of their respective columns. So this table we had already constructed using pd.crosstab. If you have forgotten, please revisit that lecture and read about it. What does pandas.crosstab do? It does exactly this. So this is actually my, my matrix. Okay. And I have calculated the total amount separately so that it will be easier for us to calculate the marginal probabilities or total probabilities, right? So this is the matrix basically. 38, 42, 82, 38 is the matrix. Okay. So let's take up some questions and try to solve it. So this is the table. What is the first question? The first question says, what is the probability that a randomly selected family is a buyer of a car? What's the probability that the randomly selected family is a buyer of a car? So a randomly selected family, total families, how much do we have? We have 200 families, right? So this total which you see has been calculated this way. This total has been calculated this way. And this has been calculated this way. Very simple. What is the probability that a randomly selected family is a buyer of a car? Okay. Out of 200 total buyer of a car. So total families who can be buyers of a car are 80. So the probability will be 80 by 20. Because it has only one restriction. What is the restriction? Buyer of a car. Whether the income is less than or greater than 10 lakhs, that has not been mentioned in the question. Right? Second, what is the probability that a randomly selected family is both a buyer of a car and belonging to income of 10 lakhs and above? Okay. So here we have buyer of a car and also 10 lakhs and above. So this will be 42 divided by 200. Simple. This is a marginal property because we have two restrictions on it. Next. A family selected at random is found to be belonging to income of 10 lakhs and above. What is the probability that this family is a buyer of a car? Wow. So now your sample space has reduced because you're talking about the sample space of people who belong to income of 10 lakhs and above, which is this sample space. 80 will be not denominator. What is the probability that this family is a buyer of a car? Now here you have to restrict yourself in this column because you have already specified the population sample space. So that is where it will be 42 by 80, not 200. So this probability will be more than 0.5, right? Around 0.6 or something, right? So this is again a marginal probability. 0.525. So joint and conditional probability. So joint probability is the probability of two or more simultaneous events, often described in terms of events A and B from two dependent random variables. So joint probability indirectly means that the two variables or two events have to be dependent on each other. The joint probability is often summarized as the outcomes, example A and B, probability of two or more simultaneous events. So P of A and B or P of A comma B. Both of them happening together. That is what we try to see. Conditional probability is a probability of one event given the occurrence of the another event. So here it's more about dependency, right? Where one event is dependent on the other. So conditional probability can be written as P of A such that B has happened. That is what is meant by conditional probability. Joint probabilities also means the same thing. It's not different, right? Okay. This is called as product rule. Importantly, the joint probability is symmetrical, meaning that P of A such that B has happened. P of A and B will always be equal to P of A, P of B and A, right? So this is called as product rule. The joint probability is symmetrical, meaning that P of A and B is equal to P of probability of B and A. Now, if you look at this here, probability of A comma B or A intersection B or AB, whatever you call it, is equal to probability of A into probability of B such that A has happened. And this probability of B comma A is given as probability of B into probability of A such that B has happened. So both these terms are actually equal. And this leads to Bayes' theorem, as I just mentioned in the previous slides, right? Okay. This we already understood, right? So from both of them, we can, from this equation, I can calculate the probability of A such that B has happened, which will be equal to probability of AB divided by probability of B. But please make a note, the probability of A such that B has happened is not equal to probability of B such that A has happened. Not equal to sign can be also written as this in Python. So I've mentioned like this, but not equal to this. So, okay. So this is not equal. So do not confuse yourself. Okay, because the dependency effect will be different. What is equal is this, the probability of both these events happening. Either I call it as probability of AB or probability of BA. That is same. But the conditional probabilities, right, such that B has happened, such that A has happened, that those two will be different. So that's it, guys. I know this is the introductory video to probability and its axioms. When we talk about multiplicative and additive, axioms or theorems. So it's nothing but this. So here, one question which may come up, I understand, is the multiplicative rule or product rule, right? So one question which may have come up, which you may ask, is the product rule. So product rule is very simple. This is your product rule, right? Product of A, probability of AB is equal to probability of BA. This is your product rule. Additive rule is what? Probability of A plus probability of B is equal to probability of B plus probability of A, right? And this came for mutually exclusive events, whereas this came from dependent events. And in additive rule, if it is independent, in the additive rule, if they are not mutually exclusive, then you have to subtract a intersection section from the total summation of probabilities. So, all right, guys. So this is all for today. Today we have covered the probability basics and the associated theorems along with it. So next video will start off with probability distribution, which is very, very important, guys. Stay tuned. See you in the next video.